Alright, what's up, you guys? It is late, 9:15 on a Sunday evening, and the last video that I uploaded was 4 principles on human behavior, and what I did was I just put my phone on a tripod on my couch, hooked up my handy dandy wireless microphone, and I pressed record. I am going to try, I haven't even shown the book so far this episode, Differential Geometry by Erwin Kreisig, reading out loud the same way. It's probably not going to get as many views, which is okay because we're in chapter 8 and there's going to be like 7 examples. I feel insecure because hasn't really been an optimal several months going on year of relationship with the gym and lifting. It's not that anything's bad, but it's like it just hasn't been a priority. So I feel like when I'm wearing a tank top on camera, if I'm not looking optimally jacked, I'm not gonna lie to you guys, I feel insecure, but I was like, you know what? All right, here we are. Like I said, 7 examples, let's get it. Section 85. Envelope of a one-parameter family of surfaces. We now consider families of surfaces without singular points and their envelopes. In this section, we start with arbitrary surfaces without singular points. The results obtained in this section will be applied to the particular case of planes in the following sections. In these investigations, we will reconsider developable surfaces from another point of view. In order to introduce the concept of a family of surfaces, we use representations of the form given all the way back in section 24.5. This is probably what I was talking about before. Capital G in terms of x1, x2, and x3 equals 0. We remember that at every point at least one of the 3 first partial derivatives of capital G is different from 0. We write for short, capital G of x sub I is equal to 0. For the sake of simplicity, we start from a particular example. A sphere of radius lowercase r whose center lies on the x3 axis at a distance lowercase t from the origin of the Cartesian coordinate system in space can be represented in the form capital G of x sub I is equal to x1 squared plus x2 squared plus the quantity x3 minus t closed quantity squared minus r squared equals 0. If we now assume t to be variable, we obtain a one-parameter family of surfaces. T is the parameter of this family, which in our particular case consists of congruent spheres with centers on the x3 axis. Every value of t corresponds to exactly one of these surfaces. We now consider a one-parameter family capital F of arbitrary surfaces, which we may represent in the form capital G in terms of x sub I and t is now equal to 0. We assume that the previous form, considered as a function of t, is of class r greater than or equal to 2, and that for every fixed value of t in this representation is a representation of a surface of class r, which satisfies the conditions stated in connection with what was in 24.5, which is related to the partial derivatives not being 0. At least one of them, that is. We assume that a surface capital S of the family capital F corresponding to an arbitrary fixed value of t intersects every surface corresponding to a value t plus h where the magnitude of h is sufficiently small. This intersection capital C star of h can be represented in the form, first A, we have capital G in terms of xi and t is equal to 0, and second B, we have capital G in terms of xi and t plus h, and this is equal to 0. Since capital C star lies also on the surface G in terms of xi and t plus h, and then minus G in terms of xi and t, which is equal to 0, we may replace the previous second case B, the representation of capital G, that is, we can replace that by a fraction where we have a numerator capital G in terms of xi and t plus h, then minus G in terms of x sub I and t, all over a denominator of h, and this is equal to 0. If h tends to 0, then the fraction equal to 0 that I just read tends to partial G in terms of xi and t partial t is equal to 0. The point set capital C represented by capital G in terms of xi and t equal to 0 and partial G in terms of xi and t partial t equal to 0 is called the characteristic of the surface capital S with respect to the family capital F. Remark: under the assumption that the limit as xi approaches xi naught and h approaches 0 of the fraction where in the numerator we have g in terms of xi and t plus h, then minus g in terms of xi and t all over a denominator of h. This is equal to partial g in terms of xi and p, partial p, evaluated at xi equal to xi naught and p equal to t. Under the assumption of this, the set capital C contains every point of the set to which the points of the intersection capital C star of h tend if h tends to 0. However, capital C will contain, in general, also other points. It may even be that neighboring surfaces of the family do not intersect at all, but nevertheless, the definition of a characteristic stated above determines a characteristic on each of the surfaces. And now here we are at the examples, and I'm going to turn off one of the lights. Example 1. The equation x3 equal to x2 cubed represents a cylinder capital Z which intersects the x2, x3 plane along a cubic parabola and whose generators are parallel to the x1 axis. By translation of capital Z in the direction of the x2 axis, we obtain a family of congruent cylinders which can be represented in the form capital G of xi and t is equal to the quantity x2 minus t closed quantity cubed minus x3 equals 0. We have that partial g partial t is equal to negative 3 times the quantity x2 minus t closed quantity squared. Hence, every surface has a characteristic given by x2 equals t and x3 equals 0, although there does not exist an intersection of any two surfaces at all. If the characteristics of the family capital F exist, and if their totality obtained by letting t assume all possible values generates a surface, this surface is called the envelope of the one-parameter family capital F. Of course, the envelope may also consist of several surfaces. In general, the parameter t can be eliminated from the definition of a characteristic, and a representation of the envelope of the form capital F in terms of xi equals 0 can be obtained in this manner. There are different possible cases which we may illustrate by the following simple examples. And so now we are at another example, example 2. In the case of the above family of spheres, we have that partial g partial t is equal to negative 2 times the quantity x3 minus t closed quantity equals 0. Consequently, the characteristic of each of these spheres is a circle of radius r in a plane parallel to the x1, x2 plane passing through the center of the corresponding sphere. From the preceding relation, we obtain t equals x3. Inserting this value in the representation of the family, we obtain the following representation of the envelope of the family. Capital F in terms of xi equals x1 squared plus x2 squared minus r squared equals 0. This envelope is a cylinder of revolution of radius r with the x3 axis as axis of revolution, for which refer to figure 90 at left. We come to another example, example 3. A pencil of planes passing through the x1 axis can be represented in the form capital G in terms of xi and t is equal to x3 minus t times x2, which is equal to 0, except for the plane x2 equals 0. As follows from partial g partial t equals negative x2, which equals 0, all characteristics coincide with the x1 axis, x2 equals 0, and x3 equals 0. That is, they do not generate a surface, and for this we can refer to figure 91 below. And another example, example 4. A family of spheres of radius t and center at the point x3 equals t of the x3 axis can be represented in the form g in terms of xi and t is equal to x1 squared plus x2 squared plus the quantity x3 minus t closed quantity squared minus t squared equals 0. We have partial g partial t equals negative 2 times x3 equals 0. The system of these two equations has the only solution x1 equals x2 equals x3 equals 0. The characteristics all degenerate into a point and they all coincide, and this is demonstrated in figure 92 at right. Another example, example 5. Concentric spheres x1 squared plus x2 squared plus x3 squared minus t squared equals 0 do not possess real characteristics at all. We will now introduce the concept of characteristic points of a surface. Let us assume that the characteristic of the surface capital S, given in the form of the function capital G in terms of xi and t equals 0, where parameter lowercase t is arbitrary and fixed, intersects every surface capital S in terms of lowercase k, given in the form of functions capital G in terms of xi and t plus k being equal to 0 of a family capital F where the magnitude of k is sufficiently small. Obviously, these points of intersection are determined by capital G in terms of xi and t equals 0, partial G in terms of xi and t partial t equals 0, and g in terms of xi and t plus k equals 0. Since g in terms of xi and t plus k equals g in terms of xi and t then plus k times partial g in terms of xi and t partial t plus k squared over 2 then times partial squared g in terms of xi and t plus theta times k partial t squared, where theta is greater than 0 and less than 1. The last equation can be replaced by partial squared g in terms of xi and t plus theta times k partial t squared equals 0, where again theta is greater than 0 and less than 1. Hence, if k tends to 0, we obtain g in terms of xi and t equals 0 and partial g in terms of xi and t partial t equals 0 and partial squared g in terms of xi and t partial t squared is equals 0. The points determined by the three relations I just read are called the characteristic points of the surface capital S with respect to the family capital F. Under an assumption similar to the limit assertion for what amounts to partial g in terms of xi and input parameter, let's say lowercase p, partial lowercase p, evaluated at xi being this xi naught point and p being equal to this lowercase parameter t, the set of characteristic points will contain the limit points of those points of intersection. It may contain also other points of the surface. It may be that the surfaces of a family do not intersect the characteristics of neighboring surfaces, but nevertheless, the three relations which I had just read above determines characteristic points on every surface. Second to last example now, example 6. In the case of the family given by g in terms of xi and t being equal to, we have a larger outer quantity, which is x1 minus then an inner quantity, x2 minus t, close inner quantity cubed, and then close the larger outer quantity squared minus x3 equals 0. We obtain partial g partial t equals 6 times a larger initial quantity, x1 minus inner quantity, x2 minus t, close inner quantity cubed, and then close the larger initial quantity, and then we have another quantity, x2 minus t, close that quantity squared equals 0. Hence there exist two families of characteristics, namely the family where x1 is equal to a quantity x2 minus t, close quantity cubed, and x3 equals 0, and the family where x2 equals t and x3 equals x1 squared. The envelope thus consists of the x1, x2 plane and the parabolic cylinder x3 equals x1 squared. Each point of this cylinder is a characteristic point of a surface of the family, as follows from partial squared g partial t squared is equal to 6 times the quantity x2 minus t, close quantity, then times we have an outer quantity 5, then times an inner quantity x2 minus t, close inner quantity cubed minus 2 times x1 close outer quantity equals 0, and the preceding two equations. If characteristic points exist and if they generate a curve or several curves when t varies, this curve lies on the envelope of the family capital F, and it's called the edge of regression of this envelope. And the seventh and final example. A family of spheres of constant radius r with centers on a curve capital C with a vector parametric representation y in terms of s arc length can be represented in the form of a function capital G in terms of xi and arc length lowercase s, which is equal to now the scalar product of, we have vector x minus the vector y in terms of s, that difference with itself. So we have x minus y of s, scalar product with x minus y of s. And then the result of that scalar product is then minus r squared. That is then equal to 0. So, as such, we find that partial g partial s is equal to negative 2 times vector y dot, scalar product with the quantity vector x minus vector y, closed quantity, and this is equal to 0. Where, as per usual, the dot denotes the derivative with respect to the arc length, lowercase s, of the curve capital C. Hence, at every point of a characteristic, the corresponding vector, which is the difference of which is the vector x minus the vector y, is orthogonal to the unit tangent vector y dot of the curve. Consequently, the characteristic of every sphere capital S, not to be confused with arc length lowercase s, is a circle in the normal plane of the curve capital C at the center of sphere capital S. The envelope of a family of spheres is called a canal surface. Remember what that is for the one problem that's going to be at the end of this section. But before we get to that problem, we're going to have two theorems, but I don't want to get too ahead of myself now. Furthermore, if the curvature kappa of capital C is positive, we have that partial squared g partial lowercase s squared equals negative 2 times vector y double dot scalar product with vector x minus vector y, then plus 2 is equal to negative 2 times kappa, then times the vector p scalar product with the vector x minus the vector y, and then plus 2 equals 0. And this is due to the formulae of Frenet, going all the way back to section 15 to remind ourselves that is where we have t dot equals kappa times p, and then we have p dot equals negative kappa times t plus tau times b, and b dot is equal to negative tau times p, where t, p, and b are all vectors. T is the tangent vector, p is the principal normal, and b is the binormal vector. Hence, the vector p scalar product with the vector x minus the vector y, then minus rho is equal to 0. That is, the edge of regression of the envelope consists of the points of the intersection of the polar axes of capital C and the corresponding sphere of the family. If rho is greater than r, the edge of regression does not exist. If rho is less than r, every sphere has two characteristic points, capital P1 and capital P2. Consequently, the edge of regression consists of two curves which have in common those points at which rho equals r. If, for instance, we take as curve capital C a circle capital K naught of radius lowercase r naught, which is greater than lowercase r, we obtain a torus, for which refer back to section 43 on tori. That was, besides the Bianchi identities, one of the single page sections in the entire book, one of the shortest ones. This surface has no edge of regression. If r naught is less than or equal to r, the edge of regression degenerates into 2 points which coincide if r naught is equal to r. The same, quote, envelope, unquote, will be justified by the following. Theorem 85.1. If the envelope, capital E, of the family capital F, for which refer back to expression 85.1 read previously, exists, then at every point of a characteristic of a surface capital S of capital F, the tangent planes of S and E coincide. That is, the envelope touches every surface along the corresponding characteristic. The proof is as follows. The vector partial g partial xi does not vanish and lies in the normal of the corresponding surface, for which refer to the remarks in connection with the formula given in 24.5 and 26.6. Maybe I'll even splice those back in from when I read those in earlier episodes. That might be easier here. Let the vector x, which has a representation, the vector x that is in terms of u1 and u2, be a representation of the envelope E under consideration. Then the characteristics are determined by t, namely t in terms of u1 and u2 being a constant. According to the definition of a characteristic of a surface, which was read previously, we have that the function g in terms of xi, which is now specifically in terms of u1 and u2, and t, which is now specifically in terms of u1 and u2, is equal to 0, and partial g in terms of, again, xi specifically in terms of u1 and u2, and t specifically in terms of u1 and u2, partial t is equal to 0. From this, we obtain that partial g partial xi then times partial xi partial u alpha plus partial g partial t then times partial t partial u alpha equals partial g partial xi then times partial xi partial u alpha, which equals 0, where alpha is equal to 1 or 2. Hence, the vector partial g partial xi lies also in the normal of the envelope. This completes the proof. We now state an important property of the edge of regression of the envelope. Theorem 85.2. if the envelope E of the family where we have a function capital G in terms of xi and t is equal to 0 exists and has an edge of regression capital R, then at every point of capital R, the tangents to capital R and to the corresponding characteristic coincide. The proof is as follows. Let the vector x with the parametric representation in terms of v be a representation of the edge of regression capital R. Then t equal to t in terms of v is determined. From now the function capital G in terms of xi in terms specifically now v, from function capital G in terms of xi now specifically in terms of v, and t now specifically in terms of v as well, equal to 0, and partial g partial t equal to 0, and partial squared g partial t squared equal to 0 for this likewise same g in terms of xi in terms of v and t in terms of v. Again, refer back to expression 85.6 above, previously read, rather. Now we find that partial g partial xi then times dxi dv plus partial g partial t then times dt dv equals partial g partial xi then times dxi dv, which equals 0. And partial squared g partial t partial xi then times dxi dv plus partial squared g partial t squared then times dt dv equals partial squared g partial t partial xi then times dxi dv equals 0. Hence, the vectors partial g partial xi and partial squared g partial t partial xi lie in the normal plane of the edge of regression capital R. Consequently, if the vector which is partial g partial xi cross product with partial squared g partial t partial xi is not the null vector, it is tangent to the edge of regression capital R. Let the vector x with a parametric representation in terms of u be the characteristic corresponding to a fixed value of t. Then, from g in terms of xi, specifically in terms of u, and t equal to 0, and partial g partial t for the same formulation of g is also equal to 0, again referring back to expression 85.5 read previously, we obtain the relations where we have partial g partial xi then times dxi du equals 0, and partial squared g partial t partial xi then times dxi du equals 0. Hence, the vector which is the cross product read previously is also tangent to the characteristic at the points of the edge of regression. This completes the proof of theorem 85.2. And now to cap everything off, problem 85.1. Obviously, one of the two principal curvatures of a canal surface of spheres of constant radius is constant. Prove that a surface with this property is always a canal surface of spheres of constant radius. The solution is as follows. Let capital S with a vector parametric representation x in terms of u1 and u2 be the surface under consideration. We assume that, for instance, kappa 1 equivalent to 1 over capital R1, which is equal to a constant which is non-zero, and that the coordinates u1 and u2 were chosen so that the coordinate curves are lines of curvature on capital S. The center of curvature corresponding to kappa 1 has the position vector y equal to the vector x plus capital R1 then times the vector n. Because of 45.1 prime, which is this formula of O. Rodriguez formulation of a normal vector where we have n sub alpha equals -1 times a fraction with the numerator b sub alpha alpha over a denominator of g sub alpha alpha, and this fraction is then times the vector x sub alpha, where alpha can be either 1 or 2, b is a component of the second fundamental form, and g is a component of the first fundamental form. Because of this, we obtain from this that the vector y1 is equivalent to partial y, partial u1. But that's not really what we want for this solution. We also want vector x sub alpha plus capital R sub alpha then times the vector n sub alpha that I just read is equal to 0, where capital R sub alpha is equal to 1 over kappa alpha, and again alpha is equal to 1 or 2, and these kappa alphas are principal curvatures, but that's the formula of O. Rodriguez. That's what we're using here in this solution. Because of that, we obtain from this what I just read, and the position of that center of curvature depends on U2 only. That is the same for all points of any fixed curve where U2 is equal to a constant. Consequently, the totality of all those centers of curvature form a curve where we have capital C that has a vector parametric representation y in terms of solely u2. We now have where the vector x minus the vector y, then scalar product with y2 equals negative capital R1, then times vector n scalar product with the quantity vector x2 plus capital R1, then times vector n2 closed quantity. This expression vanishes since the vectors x2 and n2 are orthogonal to the vector n. This means that the vector which is the difference between the vector x and the vector y is orthogonal to the vector y2. The vector y2 is tangent to the curve capital C and is constant if u2 is a constant. Hence, the curves where u2 are equal to a constant are plane. The plane of such a curve passes through the corresponding center of curvature. Plane plane, not plain. Plane. Since the magnitude of the vector x minus the vector y is equal to the magnitude of capital R1, which is equal to a constant, any of those curves is a circle with the same radius whose plane is the normal plane to the curve capital C at the corresponding point. We thus obtain a canal surface. I am sweating. Hopefully the audio was alright. I have the in-wall AC going, and it's as cold as it's going to get in here. I don't need a blanket at night because I just sweat with, if I'm being honest, even no clothes on. I'm just laying here in the nude, sweating at night. It's very hot in here. So that only took just shy of an hour. Interesting stuff. I don't know. We're getting close to the end. See you guys in the next one.